Hi, welcome back. This is not a video to explain how to build a certain machine learning model or to show you how to build a platform. This is regarding principal component analysis that we came across while we were doing our previous videos. So I will try to quickly explain what this principal component analysis is. Now for that, I'll just try to upload a set of data, our previous set of data, the iris data, into my platform. So here, once we upload, you can see in this one, we have like 4 features and 1 class. So in your data set, it can be like hundreds of features or maybe tens of features with 1 class, or you may not even have a class based on the application of your data set. Now, here, when you try to run a model or when you try to do an analysis using a wide number of features, the processing time or the required processing power is quite high. So in that case, if we can reduce our number of features, so we call it reducing the dimensionality in terms of matrices, so or like reduce the number of columns. So we can reduce the required power for our computation, and by that we can speed up our operation, or we can uh, try to reduce the computational cost, right? So now here in this case we have 4 features. Now let's consider a simple example of having 3 features, and I will give an example for like maybe 4 instances. Instances means number of records, right? Here consider these as columns as the features, just like in our example, right? So these features, I have 3 features and I have 4 data records or instances. In this case, it can be like hundreds or thousands or millions. Number of features also, it can be tens or hundreds or even thousands, depending on your case, right? Now, uh, I have put this in the form of a matrix for me to manipulate this. Now, since I have 3 features here, those 3 features, let's consider them as my XYZ axes, right? So in fact, these are XYZ axis values of 4 points, right? So XYZ axes are my features. So in that case, let's try to display this in 3D. So these are the 4 points. So these are the 4 features. Sorry, 4 records or data points that I have. So each data point has 3 features. What are the 3 features? X value, Y value, and the Z value. Right. So if I look at the values, so those are these values. One has -1, -1, 5. Other one is 1, 1, 1. The other one is 1, -1, 1. The other one is -1, 1, 5. Right. So those are 4 simple points which a certain relationship for me to show you the how this relates to a principal component analysis, right? Now, when we look at these 4 points, I can see these 4 points are somewhat on a slanted plane, right? I will show you the plane. So if I run this, that will draw a plane. So these 4 points are on this slanted plane, right? So in that case, if I want to represent these 4 points, I can represent them even using 2 dimensions. How? Because all these 4 points are on the same plane, right? This angled plane. So if I choose 2 axes on top of this plane, so these 4 points will have only values of only 2 axes, right? So though in 3D plane, these have uh, 3 axes and like 3 values to represent each data point, I can represent them on this plane with 2 axes, right? So that is reduced 1 axis, right? So see, how do we do this by axis transformation, right? So we use the technique called eigenvalues and eigenvectors in order to find the best set of axes to represent a set of data. So here, let's say first we find the covariance matrix in order to find the eigenvalues, and then we find eigenvalues here and the eigenvectors. So these eigenvalues represent the variance of the data compared to the transform set of axes. So eigenvectors, when we find eigenvectors, these eigenvectors gives the transform set of axes. So I have three axes given here, but the beauty is most of the variance, almost 100% of the variance are in these two axes, right? So this one has very little variance, that is only 10 to the power minus 16 range, right? So this is very, very, very small. Because of that, that means like extremely small. Because of that, most of the variance, so all the variance of the data, if you represent those 4 points using this set of axes, will lie in these two axes, right? So that means in these two axes. So I have sorted them. So once I sort, so I can see most of my I can represent uh, my eigenvectors with most variance as these two, right? So in my eigenvectors, I identify the vectors with most variance, so vectors which captures most variance out of the data. So if I look at this eigenvalues, about 20% of the variance is in this eigenvector, or in the last eigenvector. About 80% of the variance is in the second eigenvector, and almost 0% of the variance is in the first vector. So I can ignore the first vector, and I can consider the second and third vector for my as my axis, right? So these two will be my axis. These two will represent most of my most of the variance related to my data. So these two axes may be somewhere here. So once we have those axes, we can represent these points easily using those axes. Now, when we do that, that means we reduce one column. So I have represented the set of data using these two axes, right? So once I represent according to those two axes, so with respect to those two axes, my data points will be these ones, right? So my data points will be these ones, right? Now, once I represent my data points as this, that will still capture almost 100%. So that means out of 100, 1.3 plus 6.6 divide by the sum of 1.3 and 6.6 and 0.88 into 10 to the power minus 16. So that is pretty much 100%. Almost all the variance is captured by these two axes, and this will be my new coordinate. So here I have only two features, right? So if I go into my previous example, it is like, say at the beginning, I selected only three features, right? So if I have selected three features here, so it is like I have, instead of these three features, I have come up with new two features such that those two features represent almost 100% or 99.999 some percentage of all the variance of the set of data. However, the principal component analysis does not depend on the classes. So that is very important to know, right? Again, I will give you an example regarding that access. Now, for example, say, now we have this set of data, but my classification is based on only the y-axis. Now, say, based on my y-axis, whether it is being positive or whether it is being negative, I categorize or I classify my data set into positive or negative, or yes or no, right? So that means the first one is a no, second one is a yes, the third one is a no, and the fourth one is a yes, because this y value is negative and this y value is positive, right? Yes and no. So if I classify like that, in order to classify this data set, I only need the y-axis, right? I only need the value of y-axis. So the one feature is enough to classify this data. However, using this principal component analysis, it does not capture that requirement. It does not capture how the data is classified. It is only identifying the principal components or the set of accesses which are a linear combination of our existing accesses, of course, such that they capture maximum amount of variance, right? So in our analysis, in our machine learning, we can specify the number of principal components we need in our analysis. But in my example here, I haven't let you choose the number of principal components. Now say for example, I have this data. So when I explore, say, when I build data, it will be like this, and say, do we have any zero rows? No. Do we have any missing values? No. Do we have any duplicate rows? Okay. Yeah, we have 5 duplicate rows, so I'm going to delete them. Do we have any now? No, after I delete, I don't have. So in pre-processing, I will only apply encoding. Right, I have encoded my classes, class names, and I will divide my data set into training and testing with 70-30 split, and let the stratify, and splitting is done, and let me oversample the data. So I have 34, 34, 34 for each training set. Now when I build the model, let's ask it to apply principal component analysis, and let's use random forest. So build the pipeline with principal component analysis and go to training, train the model, and here you can see this has chosen 2 principal components. So it has chosen 2 principal components from out of the 3 features I have. It has selected 2 principal components. So based on the amount of features we have, we can decide on how many principal components we need. We can manually change it as well. In this particular application, I haven't provided that option, but in machine learning, we can select the number of principal components. And the other thing is, when we use principal component analysis, though we say it does not capture all the variance of data, that does not mean in our classification answer or in our classification accuracy, the principal component analysis will give a lesser accuracy than having all the features when we have lesser number of principal component. That is because principal component analysis does not care about classification, right? So sometimes when we select lesser number of principal components, they may get rid of certain noise that is available in the feature, so that is available in the data, because certain features may not be necessary, right? So those features may be neglected in our principal component analysis or in our principal components. Because of that, we may get better results when we use principal components, lesser principal components, of course, right? So now principal component analysis is to reduce the dimensionality, right? Dimensionality, not to increase the accuracy, right? But if you want to look into the accuracy as well, you have to do what is called LDA, which is linear discriminant analysis, right? LDA. So that will look into the classification as well. So in our principal component analysis, we try to reduce the dimensionality, and during the reduction of dimensionality, it will capture maximum amount of variance it can based on the number of principal components that it will be using for our classification. However, it will not think about the classification of the classes. In order to have a relationship with the classes as well, we have to go for LDA or linear discriminant analysis, or you can even do feature selection. So if you know how to do it, you can even do feature selection, right? Okay, so that is about principal component analysis. And so if you have any questions, you can comment, and if I know the answer, I will answer the question, or else we'll try to find the answers together. Okay, thank you.